Now, let us look into some of the problems related to frequency domain representation of the signals. It's given that there is a continuous time signal f of t which satisfies the relation Fourier transform of f of t is equal to 1 by 4 times Fourier transform of f of at is equal to j omega. We have to find the value of a satisfying this relation if a is greater than 0. We know that if Fourier transform of f of t is equal to f of j omega, then Fourier transform of f of at can be given as 1 by mod a times f of j omega by a. This is from the properties of frequency domain representation. From this we can write that f of j omega is equal to 1 by 4 multiplied by 1 by mod a multiplied by f of j omega by a. But we know that f of j omega is equal to j omega. So upon substitution, this becomes j omega is equal to 1 by 4 mod a multiplied by j omega by a. But a is greater than 0, so that implies a is equal to mod a. From this, we can write that a is equal to 1 by 2 because j omega and j omega get cancelled. So the value of a satisfying the given relation is 1 by 2. Now let us consider another problem as related to frequency domain representation of the signals. It's given that there is a signal x of t, which is a continuous time domain non-periodic signal. X of t is 1 for mod t less than or equal to a. It is 0 otherwise. It's also given that Fourier transform of x of t is equal to x of j omega is equal to 1 by pi at omega is equal to omega equal to pi. We have to find the value of a satisfying this relation. So as per this problem, there is a signal x of t given, and it's also given that Fourier transform of x of t takes a value of 1 by pi at omega equal to pi. We have to find the value of a satisfying the given relation. So we know that Fourier transform of x of t is equal to integral minus infinity to plus infinity x of t multiplied by e power minus j omega t dt. Upon substitution, this can be simplified as integral minus a to plus a e power minus j omega t dt. Upon performing the integration, this becomes e power minus j omega divided by minus j omega, and the limits to be substituted are a to minus a. So this can further be simplified as e power j omega a minus e power minus j omega a divided by j omega. So upon multiplying and dividing by 2, this can be written as 2 sine of omega a divided by omega. This is because sine omega a is equal to e power j omega a minus e power minus j omega a divided by 2j. So, but it is given that Fourier transform of x of t is equal to 1 by pi at omega equal to pi. So upon substitution, this can be written as 2 times sine of pi a divided by pi is equal to 1 by pi. So from this we can write that sine of pi a is equal to half. So pi a will be equal to pi by 6. From this a can will be equal to 1 by 6. So here we see that the value of a satisfying the given relation is 1 by 6. Please note that sin pi a is equal to half can be satisfied or will be satisfied for many other values of pi a, that is pi minus pi by 6, sorry, k pi minus pi by 6 or 2k pi plus pi by 6. So there are many values of pi a which satisfy the given relation. So there are many values of a possible, but here we have considered only a particular value of a, that is 1 by 6, by equating pi a is equal to pi by 6. So the value of a the one value of a satisfying the given relation is 1 by 6. Now let us consider another problem as related to the same, as per which there is a discrete time signal x of n which is non-periodic. It's given that Fourier transform of x of n is equal to x of e power j omega is equal to sine of 3 omega. We have to find the value of Fourier transform of n into x of n at omega equal to pi by 3. We know that Fourier transform of n into x of n is equal to j into d by d omega of x of e power j omega. So, but it is given that, so this is, sorry, this is a relation or a property that we know of. But it is given that Fourier transform of x of n is equal to sine of 3 omega, that is x of e power j omega is equal to sine of 3 omega. So upon substitution we get that j into d by d omega of sine of 3 omega is the value of Fourier transform of n into x of n. So which upon simplification becomes 3j cos of 3 omega, because the derivative of sine 3 omega is 3 cos 3 omega. So from this we see that at omega equal to pi by 3, Fourier transform of n into x of n is equal to 3j. Sorry, minus 3j. Because at omega equal to pi by 3, cos 3 omega is minus 1. So the value of Fourier transform of n into x of n at omega equal to pi by 3 is minus 3j. So from this we see that the required value of Fourier transform of n into x of n is minus 3j. It's given that there is a discrete time signal x of n which satisfies the relation phase of x of e power j omega is equal to 2k pi. This is satisfied for every omega where k belongs to z. Please note that Fourier transform of x of n is given as x of e power j omega. Then we have to find or the comment on the nature of x of n. From the given relation, we see that Fourier transform of x of n is equal to x of e power j omega, and phase of x of e power j omega is equal to 2k pi. So it means that x of e power j omega is purely real. From this, we can say that if x of e power j omega is purely real, then x of n is conjugate symmetric. So this is a known relation that if x of n is conjugate symmetric, x of e power j omega is purely real. So we could comment on the nature of the signal x of n, that is x of n is conjugate symmetric. Now let us consider another problem, as per which the DTFT of a signal is plotted as shown. So the DTFT is present in the range of minus pi to plus pi, and it takes a value of 2 at omega equal to 0. Please note that x of e power j omega that is plotted is actually the DTFT of a discrete time signal x of n. we have to find the value of the signal x of n at n is equal to 0. We know that x of n is equal to 1 by 2 pi integral minus pi to pi x of e power j omega d omega. This is actually a synthesis formula to get x of n from x of e power j omega. Of this, we see that integral minus pi to pi x of e power j omega d omega is area of x of e power j omega with omega axis. So which can be simplified as 1 by 2 pi multiplied by half into 2 pi into 2. This is actually the area of the triangle, which upon simplification is equal to 1. So from the given DTFT, we see that the value of x of n at n is equal to 0 is 1. Now let us consider another problem, as per which the discrete time signal given is h of n is equal to 1 comma 1, where the value of 1 corresponds to the instant n is equal to 0. I mean the first value of 1. From this, we have to find the magnitude of h of e power j omega, where h of e power j omega is dtft of h of n. We know that h of e power j omega can be written as sigma n equal to minus infinity to plus infinity h of n e power minus j omega n, which upon substitution can be simplified as 1 plus e power minus j omega, which is further equal to 1 plus cos omega minus j sin omega. This is because e power minus j omega is equal to cos omega minus j sin omega. From this, magnitude of h of e power j omega is equal to square root of real part, that is 1 plus cos omega whole square, plus imaginary part, that is sin omega whole square. But we know that 1 plus cos omega is equal to 2 cos square omega by 2. So this becomes 4 cos power 4 omega by 2. Similarly, sin omega is equal to 2 sin omega by 2 cos omega by 2. So this becomes 4 sin square omega by 2 multiplied by cos square omega by 2. Upon taking the 4 cos square omega by 2 common out of the square root, we get 2 cos omega by 2 as the value of magnitude of h of e power j omega. So this is upon simplifying the obtained square root using the properties of trigonometry. So we see that for the given signal x of n, the magnitude of the Fourier transform, that is abs of h of e power j omega, is given as 2 cos omega by 2. Now let us consider another problem, as per which there is a discrete time signal x of n given as 1 by 2 whole power n u of n plus 3. We have to find the Fourier transform of x of n. We know that Fourier transform of 1 by 2 whole power n u of n is equal to 1 divided by 1 minus 1 by 2 e power minus j omega. Please note that here Fourier transform of 1 by 2 whole power n u of n exists because as the sequence is absolutely summable. From this, we can write that Fourier transform of 1 by 2 whole power n plus 3 into u of n plus 3 is equal to e power j3 omega divided by 1 minus 1 by 2 e power minus j omega. This is because Fourier transform of a power n plus 3, sorry, x of n plus a is equal to e power ja omega multiplied by Fourier transform of x of n. But we have to find Fourier transform of 1 by 2 whole power n u of n plus 3, which can be simplified as Fourier transform of 8 into 1 by 2 whole power n plus 3 u of n plus 3. But we have already written down the Fourier transform of 1 by 2 whole power n plus 3 u of n plus 3. So finally the answer becomes 8 into e power j3 omega divided by 1 minus 1 by 2 multiplied by e power minus j omega. So this is the Fourier transform of the signal x of n given. Now let us consider another problem as per which there is a continuous time signal x of t given whose Fourier transform is x of j omega. And please note that x of t is conjugate symmetric. Then we have to comment on the nature of Fourier transform of t into x of t. That is, if it is real or purely imaginary or conjugate symmetric, etc. It's given that x of t is conjugate symmetric. That implies x of j omega is real. We also know that Fourier transform of t into x of t can be written as j into d by d omega of x of j omega. As x of j omega is real, d by d omega x of j omega is also real, but j multiplied by a real quantity becomes purely imaginary. So we see that Fourier transform of t into x of t is purely imaginary. So from this, we could characterize the Fourier transform. We could characterize the nature of Fourier transform of t into x of t as purely imaginary. Now let us consider another problem, as per which there is a signal x of t given as x of t is equal to 2 power minus mod t, and it is also given that Fourier transform of x of t is equal to x of j omega. So there are two statements given as related to the nature of x of j omega. The statement one is x of j omega is equal to x star of minus j omega. The statement two is real of x of j omega is equal to 0. We have to identify which of these two statements are correct. From the given signal x of t, we see that x of t is real. That implies x of j omega is conjugate symmetric. So from this we see that it satisfies the relation x of x star of j omega is equal to x of minus j omega. So the statement 1 is correct. Also we see that x of t is even. As x of t is real and even, x of t is conjugate symmetric. From this we can say that Fourier transform of x of t, that is x of j omega, is real. So imaginary part of x of j omega is 0, but please note that real part of x of j omega is not equal to 0. From this we see that the statement 2 is not correct. So we see that if the given signal x of t is real and even, then it is conjugate symmetric. In that case, the Fourier transform is conjugate symmetric and also is purely real. So using these properties, we see that the statement 1 is correct, but the statement 2 is not correct. Now let us look into another problem as per which there are two continuous time signals f of t and g of t given. Fourier transform of f of t is f of j omega. Fourier transform of g of t is equal to g of j omega. It's given that at omega equal to 1, magnitude of g of j omega is equal to magnitude of f of j omega. Similarly, at omega equal to 4, magnitude of g of j omega is equal to 4 into magnitude of f of j omega. We have to find the possible relation between f of t and g of t using the two conditions given. We know that if g of t is equal to df by dt, Fourier transform of g of t would be equal to j omega multiplied by Fourier transform of f of t. From this we can write that g of j omega is equal to j omega multiplied by f of j omega. So magnitude of g of j omega would be equal to magnitude of omega multiplied by magnitude of f of j omega. We see that the final relation we got satisfies the two conditions given. From this, we can say that the possible relation between g of t and f of t is g of t is equal to df by dt. Now, let us consider another problem as per which there is a discrete time non-periodic signal given as x of n is equal to 1 by n squared. It's given that Fourier transform of x of n is equal to x of e power j omega. There are four options given, which are 2 plus 3j, 1 plus j, none of this. We have to find which of the options given wouldn't correspond to a value of x of e power j omega. We see that x of n is equal to 1 by n square is real and even. From this we can say that x of n is conjugate symmetric. We know that if x of n is conjugate symmetric, Fourier transform of x of n is equal to x of e power j omega is real. So x of e power j omega is real for every omega. So from this we can say that A, B and C are not the possible options as they are imaginary numbers. From this we see that option D is the correct answer. Now let us consider another problem as per which there is a signal x of n given as 1 by 2 whole power n multiplied by u of n, and it is given that the derived signal y of n is equal to x cube n. It's derived from x of n as x cube n. If Fourier transform of y of n is equal to y of e power j omega, find the value of y of e power j0. We can see that y of n is equal to x cube n can be written as 1 by 8 whole power n u of n. This is by cubing the 1 by 2 whole power n u of n. So from this we can say that y of e power j omega is equal to sigma n equal to minus infinity to plus infinity y of n e power minus j omega n. So y of e power j0 upon substituting omega equal to 0 becomes sigma n equal to 0 to infinity 1 by 8 whole power n. So this upon simplification becomes 1 divided by 1 minus 1 by 8, that is equal to 8 by 7. From this we see that the value of y of j0 is 8 by 7. So we can say that the required value of y of e power j0 is 8 by 7 from above. Now let us consider another problem as per which there is a discrete time signal x of n whose DTFT is given as x of e power j omega. It's given that x of e power j omega is 1 for 0 less than or equal to mod omega less than or equal to pi. It's given that there is another signal y of n, which is derived version of x of n as n into x of n, whose Fourier transform is given as y of e power j omega. We have to find the area of apps of y of e power j omega with omega axis in the range of minus pi to pi. We know that Fourier transform of y of n can be written as Fourier transform of n into x of n, which is equal to j into d by d omega of x of e power j omega. From this, we can write that apps of y of e power j omega is equal to apps of d by d omega of x of e power j omega. Upon plotting x of e power j omega in the range 0 to pi, we get that x of e power j omega as shown. Sorry. So we see that for minus pi to 0, the slope is 1. For 0 to pi, the slope is minus 1. I'm sorry. So the plot of x of e power j omega looks as shown below. It is actually omega from minus pi to pi. And please note that the plot is of slope 1. From this we see that d by d omega of x of e power j omega will have a value of 1 because of the slope of x of e power j omega. From this we can show that apps of y of e power j omega is 1. This is for 0 less than or equal to omega less than or equal to pi. From this we can say that the area A is equal to 2 pi, which is the width, multiplied by 1. So the answer is 2 pi. So the area of apps of y of e power j omega with omega axis in the range of minus pi to pi is 2 pi. Now let us consider another problem, as per which there is a signal x of t which is given as 1 by 2 whole power mod t. So based on this, we have to comment on the Fourier transform of x of t, that is x of j omega. We see that the given signal x of t is purely real, and we also see that the given signal is even. From this we can say that x of t is conjugate symmetric. As x of t is conjugate symmetric, Fourier transform of x of t, that is x of j omega, is real. So we can say that the imaginary part of x of j omega is equal to 0, or phase of x of omega is equal to 2k pi, where k belongs to z. So from the given x of t, sorry, for the given x of t, we can characterize x of j omega as that imaginary part of x of j omega is 0, or the phase of x of j omega will be 2k pi, where k belongs to z. Now let us look into another problem, as per which there is a continuous time signal given as x of t is equal to e power minus t. We have to comment on the nature of Fourier transform of x of t. Here we see that the signal x of t is equal to e power minus t is real. So we know that if x of t is real, Fourier transform of x of t is conjugate symmetric. That is, it satisfies the relation, um, sorry, a capital X of j omega is equal to x star of minus j omega. From this we can say that magnitude of x of j omega is equal to magnitude of x of minus j omega. So here we see that the magnitude spectrum is symmetric or even. So these are the properties that would be satisfied by Fourier transform of x of t if x of t is real. Now let us consider another problem as per which there is a continuous time signal x of t given. Please note that x of t is non-periodic and there is a derived version of x of t given as y of t is equal to x of 2t minus 3. If Fourier transform of x of t is x of j omega, find Fourier transform of y of t, that is y of j omega, in terms of x of j omega. We can find the Fourier transform of y of t as integral minus infinity to plus infinity x of 2t minus 3 e power minus j omega t dt. Substitute 2t minus 3 is equal to p, that implies t is equal to p plus 3 by 2. Also note that dt is equal to dp by 2. Upon substitution, we can simplify the given relation as integral minus infinity to plus infinity x of p multiplied by e power minus j omega multiplied by p plus 3 by 2 dp by 2. So this can be further simplified as 1 by 2 multiplied by e power minus 3j omega by 2 integral minus infinity to plus infinity x of p multiplied by e power minus j omega by 2 into p dp. So this can be further simplified as 1 by 2 e power minus j omega 3 by 2 multiplied by x of j omega by 2. So we see that the derived version of x of t, that is y of t is equal to x of 2t minus 3, has a Fourier transform of 1 by 2 times e power minus j3 omega by 2 multiplied by x of j omega by 2. This is actually y of j omega. From this we can also deduce that abs of y of j omega is equal to half multiplied by x of j omega by 2. Sorry, half multiplied by abs of x of j omega by 2. This is because of the reason that e power minus j omega 3 by 2 has a magnitude of 1. Also we can write that phase of y of j omega is equal to phase of x of j omega by 2 minus 3j omega by 2. This is because of the reason that e power minus j3 omega by 2 has a phase of minus sorry 3 omega by 2 has a phase of minus 3 omega by 2. So because of which phase of y of j omega can be written as phase of x of j omega by 2 minus 3 omega by